Good morning, everybody, and thank you for joining today. I will give it a couple of more minutes just to allow people to join the webinar, and then I'll make a start. Please note this meeting is being recorded, just for future distribution, and there's also some people that weren't able to attend today as well.
Welcome. Good morning.
Good morning.
Morning.
I'm just going to give it another minute just to allow other people to join. Just a brief reminder, this meeting is being recorded. If I could just ask you just to make sure that your microphones are muted, and just allows us then to distribute this out later, this recording later on, to those who would like it, and also to those who aren't able to attend today. So I'm just going to give it another minute before we start. Okay, so we'll make a start. Thank you very much, everybody, for joining today. Just a brief reminder that this presentation is being recorded. If I just ask you to keep your microphones muted for the time being, please feel free to use the chat to ask any questions. My colleague Kirsty Miller is monitoring the chat as well. So yeah, unfortunately, I can't see the chat as it happens. So yeah, if there are questions towards the end, I'll just ask you to ask them, and Lee will answer them. Then, my name, for those of you are not aware, my name is Greg Wainhouse. I'm the Business Development Manager for Water Applications at Bürkert UK. Been with Bürkert since 2015, so I'm approaching 10 years of service. Located in the centre of the UK in Coventry, where our regional office is nearby in Cirencester, about an hour and a half away. And I'm responsible for water and wastewater treatment applications, and have a specialist in analytical parameters for the UK as well. We'll start off with a brief introduction for those who are not, excuse me, familiar with Burkert. We'll then have an introduction to the OA lab. We'll also have a look there at some of the examples of where chlorine is added and also removed, or dechlorination as we refer to it as. We'll have a look at traditional chlorine detection methods and their deployment with applications such as carbon filters. We'll then go on to have a look at the MSO2, which we see as the next generation of chlorine measurement and detection. And then we'll also have a look at where the MSO2 has been used, or is being used, I should say, at the moment. There are some ongoing applications where we're looking at data at the moment, so we'll have a look a little bit closer there as well. So as a brief introduction to Burkert, we're a global company of about 3,700 people worldwide. We turn over about 710 million last year. We put a lot of our returns back into the business, as well in terms of research and development, at just under 7% last year. We were founded in 1946 by Mr. Bürkert, who is no longer with us, but we are and we do remain a family-owned company. Which allows us to reinvest all the profits back into the business, back into developing solutions, but also into our people as well. We operate globally, all the way from the Americas, all the way across Europe, South Africa, Middle East and right across to the Far East as well, Asia, Japan, Australia, New Zealand as well. And what we learn from each of those markets, we're able to quite often transfer into local markets as well. But we still find that there are some, difficulties, some nuances between each market as well. So it becomes a little bit of a learning kind of moment for us all. For those who aren't familiar with our products, the screen is what I'd like to refer to as the cheese wheel of products. We started out manufacturing solenoid valves. That's what most people know us for. Mr. Bürkert himself developed a very unique diaphragm valve, an isolated diaphragm, and that protected corrosive gases from getting up into sensitive electronic areas. And that design was then developed even further, and we've now developed a fair few different designs of solenoid valves. We now also manufacture process valves up to kind of 4-inch. We also have control valves. We also have a range of pneumatic valve islands as well. So if you want to pilot larger process valves, a number of them, then we can put the pilot valves on an island and put them in a cabinet for you as well. And then we come on to things like our sensors. So we have flow sensors, analytical water quality sensors. We have pressure sensors, temperature sensors as well, and level sensors in our portfolio. And then number 8, we have our microfluidic range. So this is where we have, kind of microfluidics down to like 0.1 of a millimeters in diameter orifice size. So very, very tiny orifices for things like analysis of things like blood hematology, for example, DNA analysis. And then finally, number 9, we have our mass flow devices. So things like mass flow for gases, mass flow for liquids as well. So we've got quite a broad spectrum, broad portfolio as well. We're going to look a bit closer at our water quality portfolio, and we'll start with an introduction to the OA Lab range of products. OA Lab is a really flexible clean water quality monitoring system, and I do highlight this is for the clean water market. We're not looking at the wastewater market. The example you can see in the picture there is a panel with 7 sample lines coming in from various different parts of a drinking water plant, which I believe was in Germany. And within that panel, which is only about 1 meter wide, we have got 14 sensors inside of it. That's 14 analytical parameters, for example, pH, conductivity, ORP, chlorine maybe be in there as well. The one thing I do know that's in there are 2 turbidity sensors. So that's measuring the cloudiness of the water, if you like. And I know that because you can just make out these big square boxes. Those big square boxes actually are cleaning facilities, automatic cleaning facilities. They're not the turbidity sensor. A traditional turbidity sensor is a big stainless steel tube, about 12 inches in length, and just 2 of those would have filled this cabinet alone. But the fact that we've got 2 of those turbidity sensors and another 12 sensors in there just shows how compact and small a footprint this particular portfolio can offer. Now, I know that this one particular system as well, it replaced a 4-meter sampling wall. And it also provided not only a big space-saving solution, but it also provided a big significant cost down for the client as well, over replacing the traditional type of sensors. So it just gives you kind of a very I must admit it's quite an extreme example, but it gives you an idea of just what this system is capable of doing. On the other end of the scale, a much more basic solution, you can see in the top right hand corner an application for just monitoring pH and chlorine. So you can see these 2 cubes up on the right hand side. Let's see if I can get a pointer in here for you. Laser pointer, there we go. You can just make out the 2 cubes up here. So one will be chlorine and one will be pH. And then we've got an industrial gateway to give you something like Ethernet or Profibus, and then a display there as well. All this was pre-mounted for our customer. I believe it's for an application in France. All pre-mounted by Bürkert on a polycarbonate board. So that the customer just simply connected his fluidic connections, the electrical connections, comms, for example, and then just it was kind of like a plug and play scenario. all the components that you can see there are actually IP65 rated, so it didn't need a stainless steel enclosure or anything like that. And because it was indoors, customer was just happy as it was. As it happens, the customer actually wanted to include turbidity further down the investment line, and because everything is operating on an internal bus network, which is actually based on CAN-open, it was really easy for us to actually just expand the network and then add on the turbidity sensor and the cleaning system that you see here. This is a bubble trap and a filter and a regulator. It was really easy just to expand those very quickly, add them onto the bus network, and then add those onto the 7-inch touchscreen display that you can see there. So not only is it easy to deploy in very small applications, it's also really easy to expand on as well. This is another application that we did for a UK customer. It was based in a container, and this particular customer wanted to be able to monitor the performance of some filters that they had developed and were testing. And they needed 5 turbidity sensors. Now, if you remember, we talked about turbidity right at the start of this part of the presentation. We said, we have these big kind of 12-inch long stainless steel tubes. And that was going to be too much for this particular client, because they wanted to install everything in this container and they were already pushed for room to start with. And this particular panel, you can see on the right hand side, we fitted 5 turbidity sensors in one of these panels, only about 700 mil wide. And rather than having 7 cleaning mechanisms, we just had a single cleaning mechanism to keep the optical sensors clean, but we deployed 5 of our solenoid valves, 3-2 solenoid valves, and we had a graphical program on board as well that basically in turn routed the cleaning chemicals to each sensor individually in turn, and that helped make the panel smaller. It also helped reduce the capital expenditure. Bürkert built everything. We did it all under a single ID for the panel, so the customer just had to order one and then be able to install that in the container. And we also provided all the bubble traps as well, because bubbles can attenuate, or it can dissipate the refract. That's the word I'm looking for. Sorry, it can refract the light source and give false readings. So we have to remove all the bubbles from the water. And yeah, that's what those bubble traps are for. Then we pre-mounted all those for the customer as well, so they can just put it in the cabinet in a nice neat format as well, so you can just see it tucked up on the left hand side of the top picture there in there. And then finally, another final example. This is again for measuring chlorine. This time this is monitoring the outlet of a carbon filter, protecting a reverse osmosis membrane. Now, reverse osmosis membranes are very susceptible to chlorine attack. When the chlorine attacks the adhesive, the membrane starts to become unwound, and then you start to then get impurities passing through, and that's what you want to try to avoid. So remove all the chlorine as much as possible through a carbon filter, for example. And so for this one, instead of a free chlorine sensor, is what we refer to as a zero chlorine sensor, because the carbon filter should have removed all the chlorine from the from the supply water. And that's what we're doing here. Again, all IP65 components on the polycarbonate backboard here. And then we've just got a polycarbonate housing above it for the I/O systems, because this is a slightly different type of I/O system. Again, a gateway providing Ethernet-based output. We've also got some digital input cards here, because we have a flow verification sensor, you can see in the middle here. This is just providing a pulsed output to a digital input card, and then that's going out onto the Ethernet signal as well. As it actually happens, this particular pharmaceutical customer has gone out to deploy this particular solution on a number of different sites as well, globally as well, because they've gained confidence in our solution. So the technology behind what we're offering here, and the success, if you like, of our portfolio, we have something called MEMS, which is micro electrical mechanical sensors on chip, which are based within the compact transmitter. So these cubes that you see here, they're about 2 inch long, 1 inch wide, very, very small compact systems. There is a small chip inside each one of those based on the different parameter that you're trying to detect inside of there. So the fluidics come into the transmitter, go across the sensor, and then back out again. Now, each of those transmitters is based on a digital protocol. I mentioned before, we use CANopen, an industrial version of CANopen, and that allows for equal data sharing amongst all the kind of the devices on the network. There's no master-slave configuration, so all the data can be shared equally amongst the devices. So it doesn't matter where you plug in next to any of these devices on the bus. You can pull off data about everything that's on that bus. As well. We have standard gateways as well to provide Ethernet-based communications. I mean, if your PLC can take a CANopen signal, then you can take those sensors directly into the PLC. Otherwise, you can use one of our gateways to give you either Ethernet, Profinet, Modbus, TCP, or even Profibus, and we've got a few other flavors as well. We also have options for things like 4 to 20 milliamp outputs and inputs as well, or simple transistor switched switches as well, but they are additional extra on top of the gateway. So the gateway generally tends to be our standard. Each cube, and this is quite unique, each cube only requires 9 liters per hour per cube. Now, if you were to take something like a standard glass probe, say for example, and that typically would tend to use something like 2,000 liters per hour of water, which you send to drain. That is a lot of fluid. That's based on a 1 inch line at 1 meter per second velocity. So 2,000 liters per hour just for a glass probe. Whereas for our pH sensor, we're only using 9 liters per cube. Now, if you were to pair that up, if you were to have pH and chlorine, we would double that. So it would be 18 liters per hour. But even so, that's still significantly less volume than say, than 2,000 liters per hour. So very, very small quantities of water that we're using. All the calibration data as well, when we calibrate our cubes, they're all stored on the internal EEPROM as well. Whereas with traditional glass probes, say for example, you have to calibrate the probe with the transmitter, and if you remove that probe and you go and pair it with a different transmitter, you have to recalibrate them again. Now, there are some manufacturers now that are putting little chips within the within the glass probe that allows you then to do the calibration and then move it about. But traditional glass probes don't have that. But whereas we do, we've developed an internal EEPROM, so you can take the cube off the backboard, off the fluidic manifold, and then go and put it with any other system of a Bürkert system that allows you, then just takes that calibration data with it. So you can take it back to the lab, calibrate it in the lab, put a spare one online, get your process back up and running quicker. We also have LEDs on the front. You can see them, they're turned off at the moment because they're not on the manifolds, but you can just see these LEDs on the front. They will change different colors based on the NEMER NE 107 standards. So they will change, red, which is a complete failure. Green means operation and measuring. Yellow and orange and blue will all have different status requirements, but they are industry standards now as well. But you can see them individually at a distance as well. So if there's a problem with the pH, it is just isolated to the pH, or if it's the chlorine, it would just be the chlorine that would be changing its status. So the range of parameters that we do have available in this kind of compact cube format is pH or ORP, or what's referred to as redox. We also have conductivity, free chlorine, zero chlorine, chlorine dioxide, and also turbidity. We also have iron, nitrate, and SAC UV254, sorry. They are slightly different designs. They're not the compact cubes that you see on in front of you, but they do embed as part of the internal bus network that we have very easily. So you can get all that data onto the gateway, but they are slightly different designs. Some of them are bigger probes, some are a slightly bigger cube design as well. Some use reagents, some don't as well, but it just gives you an idea of the portfolio that we have that we can integrate together. So we'll go on to look at now chlorine. Where is chlorine added? Well, we could be looking at anything like municipal drinking water supplies, things like hospitals, or even borehole supplies as well. And each one has their own requirement for adding in chlorine. So with municipal drinking water, you need to ensure complete disinfection across the distribution network, right up to the tap, or the consumer's tap. Within hospitals, because they want to control the amount of chlorine going across some of these hospitals. Some of these hospitals can be very, very big. So, if you just rely on the network distribution, there may not be enough chlorine to get to the furthest tap on the other side of the hospital wing. So it's quite often you'll remove the chlorine, then add in a known volume of chlorine to get to the furthest point as well. In borehole supplies, specifically in industrial use as well, some like to disinfect the water, even though it's come out of a borehole and is thought not to contain high levels of bacteria. They may still want to disinfect it just to give them that confidence that it is completely safe to use. And it's the same for things like food and beverage as well that are using borehole supplies. So we've talked about where we add chlorine. What about removing chlorine? Well, in pharmaceutical and healthcare, they may be using a borehole supply where they're adding it in, but actually the chlorine can, as I mentioned earlier, can easily damage things like reverse osmosis and can also have a detrimental effect on a process like electrodeionization, so EDI. Systems as well, and that will lead to damaging the system and then letting unwanted impurities pass through to the process. Now, in things like healthcare scenarios, where you're doing things like kidney dialysis, you have to ensure that all of the chlorine is removed because chlorine can seriously damage a patient's kidney. So you have to remove all of that chlorine completely. So you have to have some way of measuring to make sure that all of the chlorine has been removed. You have to have an effective way of doing it as well. In food and beverage, chlorine can damage and affect the taste of raw food ingredients, whether it be salads or things like live cultures. We have a lot of live culture products on our supermarkets nowadays, things like yogurts. You have the good bacteria products as well, it's good for your gut. And also you have things like yeast, which is used in the brewery process as well. So you need to make sure that you're not killing off the yeast as well. Otherwise, you won't make good beer. And also in industrial applications as well, things like chlorine. Chlorine can corrode semiconductor wafers, and that increases the amount of scrap product that a semiconductor manufacturer can develop. And the semiconductor industry is one of the heaviest consumers of water at up to 3,000 litres per wafer, which is a huge, huge volume. And especially this is where you've got countries where water is becoming a scarce resource. It's really, really important to maximize and the amount of water that you are using per wafer, reduce the consumption, improve the efficiency of water. So you want to reduce the scrap in the process as well, so you're not using too much. And obviously one way to increase that is to remove the chlorine, so you remove the amount of scrap caused by that corrosion as well. How is chlorine typically removed? Well, quite often you'll use things like UV systems. UV systems can be quite high capital expenditure, high energy intensity, but they are highly effective and allow high flow throughputs. We see a lot of these in municipal wastewater areas as well, where they're trying to kill off large volumes of bacteria. UV systems also really good at removing chlorine as well in drinking water application. So a process called photodegradation or photolysis, which breaks down the chlorine. We also see things like carbon filters. They are available in various different sizes, from under-the-counter applications right through to very, very large silos. They come on the back of trucks and are offloaded, and then the water supply is connected up. Now here in the carbon filters, the water absorbs the chlorine as the water trickles down through the carbon. You do typically tend to see slower flow rates. And also you get this process called channeling, and this is where the water essentially erodes a water channel through the carbon, and the chlorine doesn't get absorbed. And as a result, you tend to see the chlorine level suddenly increase. Now the way to get around that is to then backwash the carbon, and then that stops that alters the structure of the carbon, removes those channeling processes, and then starts to absorb the chlorine back through the carbon now as well. And then the other way that we see chlorine removed is through chemical dosing processes, such as potassium metabisulfate, sodium bisulfate, which neutralizes or removes the chlorine from the process as well. But if you're an end user, you will kind of consult with a system integrator or an OEM to determine what is the right process for you, whether it be on the amount of chlorine that's coming in the process, or the amount of bacteria that's coming through the process, or if there is through volumes. We can't tell you which is the best way to do the chlorine removal, but what we can do is tell you the best way to detect the chlorine coming into the process, but also most importantly out of the process as well. So how is chlorine traditionally detected? Well, on applications, we sometimes do see handheld devices. So a process called colorimetry devices, where what you will see is a sample being taken offline, then mixed with, say, for example, a tablet, something like the Lovibond MD100, which is very, very common device across the various different industries. They'll take that, mix it with the tablet, wait for it to dissolve, and then the water, the media, will change color based on how much chlorine there is in the water. And the deeper the color change, the higher the concentration of chlorine. And this is what's referred to as a DPD method. Now, if you are regularly monitoring chlorine, these devices typically can get used for calibration and verification of online solutions, continuous measurement or online solutions, rather than doing a hand gram sample every couple of minutes or once per hour. Quite often we see these used either once a day, once a shift, maybe even sometimes once a week. So they're not continuous online devices. They're there just to grab a sample and measure it and verify the process. There are online versions of the DPD method. There are various different manufacturers that offer online colorimetry analyzers. Bürkert is not one of those, I will admit, not for chlorine at least anyway. We do have an iron sensor which uses colorimetry method. But it is essentially exactly the same process as the handheld device, but it's just automated. Those automated processes, yep, they'll take a sample, they'll mix it with a chemical rather than a tablet. Again, you wait for the chemical reaction, the color change, and then you measure the color depth with a photometer, an online photometer. Inside, if you open up one of these, you would see things like pumps, valves, the photometer itself as well, and then you have an onboard transmitter providing a measurement. The one key thing to say, though, is that it's not a continuous method, very much like the handheld methods that you would maybe do once a day, once a shift. These particular analyzers, they can do a measurement every couple of minutes. So it's still not a continuous measurement. It's still only taking a measurement every 2 minutes at the very, very maximum, but it's using a reagent at the same time, and that reagent costs money at the end of the day. Another method that we generally tend to see is an ampermetric sensor. Now, Burkert do have ampermetric sensors in our portfolio, things like our type A232, and there are various different manufacturers on the market that offer traditional ampermetric probes like you see on screen now. That's a Burkert type A232. They are typically located in a manifold, so you can just about see the manifold here and then the probe inserted in the manifold. And the manifold helps to reduce the effects of pressure fluctuations. Quite often we'll get customers telling us, oh, it's a very stable flow rate, stable pressure. But if we were to put a pressure sensor or a flow sensor on there, I guarantee you we will see changes in the process as pumps come online, as valves divert fluids in various different directions, or somebody goes up and grabs a manual sample for the DPD verification process. There will be some fluctuations. So that's what the manifold is there to do, is to remove those pressure fluctuations. Now the ampermetric probes, they use electrodes to detect the presence of hydrochloric acid ions. In front of those electrodes, you then have an electrolyte. And that electrolyte, potassium chloride, not only protects the electrodes from scaling by preventing the media getting onto the electrodes, it also buffers the liquid to a pH common level. And then those electronics, then they detect the hypochlorous acid and then convert that measurement into a concentration of chlorine. Now, the reason why the pH there is as a buffer is because the amount of free chlorine changes with pH. So say, for example, at pH 5.5, pH 6 approximately, the amount of hypochlorous acid in the media, there will be pretty much 100% of that chlorine is freely evactive and available to disinfect the media. However, when you go up to say pH 7.5, the amount the concentration, the percentage concentrations drops dramatically, almost, kind of like 10 or 20%. I don't know the value off the top of my head, but say, for example, 10 or 20% of the available chlorine is actually effective hypochlorous acid. So that's why we have to measure or buffer the amount of pH to a common level to detect that kind of that amount of free available chlorine to disinfect. So it's very, very important that that electrolyte also remains clean, clear, and pure as well, because it's also doing a job. It's doing two jobs in there as well. So they're really, really important. There is another type of probe that we can also deploy to measure chlorine or to detect chlorine called ORP, oxygen reduction potential, or redox, but it's not a direct measurement of chlorine. It's detecting whether the media that's in there is an oxidizing species. And we'll touch on that a little bit later, but it's not an actual measurement of chlorine. So we're not going to include that as a method of measuring chlorine. Now, some of the issues that you can face with these, some of the device value propositions before we look at the negative side. Sorry, the colorimetric handheld analyzers they're relatively low cost. There's no installation requirements, but they can produce very accurate results. With things like online colorimetry analyzers, they are high repeatable systems. They're very easy to install. Quite often, you just need to give them a sample line and a drain line, switch them on, provide them with some power, switch them on, and then set them up with the online, with the transmitter that's embedded in the system, the controller that's embedded in the system, I should say. They quite often come with automatic cleaning systems sometimes as well. They generally tend to have low recalibration requirements. Quite often there is a recalibration system on board as well. They're also not reliant on pH changes as well. They can also be used for these zero or trace chlorine applications, downstream of something like a carbon filter or a UV removal system as well. What I will highlight, though, is both colorimetry and ion analyzers, although they are very accurate, highly repeatable, have low recalibration requirements, that is when they are maintained properly, regularly, and also used properly as well, used in the right kind of environments as well, because you do get things like biofouling, you do get scaling sometimes inside of these, so they do need maintenance. So they're only repeatable, they're only accurate when they are looked after and maintained. Now, ampermetric sensors on the other end of the scale, they are low cost traditionally compared to online analyzers, but the maintenance skill requirement is also quite low, but requires training. So with ampermetric probes, you do have to replace the potassium chloride, but actually compared with colorimetry analyzers, you generally tend to find that it's the OEM that recommends that they do the maintenance, because you've got things like pumps, valves, You've got the reagents as well, which you have to be careful how you handle those as well. So we say that the skill requirements on ampermetric probes is a little bit lower compared with online analyzers. And we do have dedicated ranges of devices for both free chlorine and trace chlorine, as well as chlorine dioxide. So you have to make sure you get the right probe for the process. Now, some of the constraints with these technologies, apologies, I jumped ahead slightly with the last slide, but some of the constraints that we have with these traditional methods of measuring is, for example, as I've highlighted a few times with the handheld devices, is that they are not a continuous measurement. You do have to have training, because sometimes even a small change in the volume, the sample that you take off, can actually make a difference to the measured value. So you have to make sure that you get just the right amount up in the vial where you take the sample every single time. Because if that changes, although the DPD tablet generally tend to be a controlled device or additive that you put into it, the sample that you're taking needs also to be controlled, because if that's not controlled, that changes the concentration that becomes measured. So you do need to make sure that you get training on how to take a sample for the colorimetry handheld device. Now, with the online analyzers, as I've already highlighted before, it's not actually a continuous measurement, because it's taken a sample offline, it's then doing the mixing with the chemical, and then it produces the measurement of that sample and that mixing reagent. So it's not a continuous measurement. So there could be peaks and troughs of chlorine either going into the process or coming out of the process, whatever that filtration process is. So we say that the T90 time, so that's the amount of time it takes to get from 0 to 90% of the measured value. We could say that the T90 time of a colorimetry analyzer is about 2 minutes, but that's at its very, very maximum, because you are consuming reagent. Now, typically the reagent that's installed in one of these colorimetry analyzers, if you're taking a sample every 2 minutes, would be consumed within a month. So you're having to purchase new reagent every month to make sure that you get that 2 minutes measuring time. So it's quite often that operators will reduce the frequency of sampling to conserve the reagent, to get it to last, say, for example, 12 months. So it could be that they're actually only taking a measurement maybe once an hour or once a shift. And that way you're not capturing all of the chlorine that's been coming through onto the filtration process or after the filtration process. So you may be missing peaks and troughs of chlorine. So how do you know how effective your chlorine removal process actually is, or how much is coming onto it? So how often do you need to do maintenance on that chlorine removal process as well? So these are things to have to consider. You need to have trained personnel to service the analyzer. And this is why I say that it needs to be, normally it would be the OEM that does, or a contractor that does the maintenance of these colorimetry analyzers. And that can often be expensive as well. Spares, we talked about pumps and valves, being used on these analyzers. Quite often they can be quite expensive as well. Now, with ampermetric probes, they are by no means at all perfect. Far from it. As a supplier of ampermetric probes like the Type A232, we understand the challenges that go behind these. Things like higher installation costs and effort, for example, because you've got to have the manifold, you have the sample line, you have the inputs, the outputs. There is also things like a settling in time for these ampermetric probes traditionally as well. And they can also be influenced by things like the pressure changes. So you have to consider those and make sure that you compensate for those as much as possible. The potassium chloride in front of the electrodes also can be poisoned, which results in sensor drift. So you have to regularly calibrate the device on a regular basis. You also have things like scaling of the electrodes. As the potassium chloride becomes poisoned, and also there's some membranes in front of the electrodes and in front of the other side of the electrolyte as well. They have to be regularly cleaned and cleared of any scaling as well to prevent drift. And And all that as well can also lead to inaccuracies of measurement as well. So they are very, very prone to drift as well when they're not calibrated and maintained regularly. Now, the T90 time of something like a traditional ampermetric probe can also be about 2 minutes as well, but it also does depend on the quality of the electrolyte and the membrane as well. So there's various different things to have to take into consideration. And again, that T90 time could be missing the peaks and troughs that are coming through the process as well. Now, ampermetric probes are also quite difficult to measure in low concentrations of chlorine. They're also difficult to recover from zero chlorine conditions. They suffer from an issue called polarization. And this is where it doesn't see chlorine for long periods of time. As soon as a slug of chlorine comes through, it doesn't always detect it because of polarization. So quite often, operators will also regularly inject a known concentration of chlorine to try to prevent and also try to detect the polarization issues. But of course, if you're going to automate that regular injection, that's more capital expenditure. So this is where some of the higher installation cost also comes from. Now, when I first started looking at ampermetric probes and started talking about chlorine many years ago, we had several customers come to us and say to us, we have to maintain and calibrate our ampermetric probes every 12 weeks, every 3 months. Now, I thought when I first heard that, I thought that just must be a one-off. But we hear this time and time again because they can't be certain that ampermetric probes are doing the best thing because of poisoning of the electrolyte, scaling of the electrodes, for example, as well. So they have to take all of these things into consideration and regularly calibrate and maintain the probes. Every 12 weeks, that's a lot of maintenance. So where do we see these technologies deployed? So if, for example, we see something like a carbon filter here to remove the chlorine from incoming Towns water, for example, if you were to have an ampermetric probe, yes, you could have it before an RO, after a carbon filter, but you've got to have that additional chlorine sample being injected onto the ampermetric probe on a regular basis to detect polarization. We've also got that T90 time of 2 minutes. So you can put them in there, but they're not great. We do not recommend them to protect something like an RO or an EDI process. Instead, you would put something like a colorimetric analyzer in there instead. So this is where, you know, we haven't got issues with pH drift, we haven't got issues with electrolyte drift. You're using an you're using a colorimetric solution, but then you've got the T90 time of it taking the sample every 2 to 3 minutes, or even longer if you're trying to conserve the reagent. So it's not something, again, we would recommend, but it's the best of the best of a worst case scenario, so to speak. Where we do often see ampermetric sensors is being used on the inlet to the incoming water, where it's less of a concern, where it's just good to know that you've got chlorine coming into the process. So you can be confident that the carbon filter is removing or it's carrying over because there is something coming into it on a regular basis. So there's no problem with using something like a free chlorine probe on the inlet to the incoming water. However, in this scenario, quite often you would have, first of all, you've got 2 different technologies. You would quite often have 2 different transmitters with different menu layouts. You've also got a high capital expenditure because, you know, you've got 2 different technologies, 2 different methods of delivering liquids to it, both having different consumptions. So there's a lot of things there to have to consider that would add cost. It's also not a continuous measurement of the post carbon filter or, you know, kind of post chlorine removal method. And that's the most critical thing. If you're trying to build up a picture of how much chlorine is getting onto the RO or getting onto the EDI or any other process downstream, it needs to be a continuous measurement or a measurement with a very, very low T90 time. So even the colorimetric analyzers aren't great for protecting the RO and the EDI process. So what would Bürkert recommend? Bürkert would recommend using our MSO2 chlorine sensor and zero chlorine sensor. we can provide a solution to monitor both before and after on a common backboard, or going into two sets of sensors. Here we have got very low sample volumes. Even something like the ampermetric probes, even they will use, kind of 18 liters, 30 liters per hour of water. Still, 30 liters per hour versus 18 liters per hour is still quite high volume of water going to drain. So with our solution, we have low sample volumes, which we talked about at the very start of this presentation. We have the free chlorine measurement coming into the carbon filter, which we're able to measure. We'll also have a pH sensor, an active pH sensor, because our free chlorine sensor doesn't have any electrolyte in the cube at all. So we have to use an active pH sensor. That actually improves the accuracy of the chlorine measurement as well. So there is a little bit of a benefit by using a live pH probe. And on the post-carbon filter, we can also use our zero chlorine measurement sensor. And again, this is a sensor that doesn't use reagents. It's not something we have to regularly replenish, have to look after on a regular basis like a reagent. But most importantly, it is a continuous anion analyzer. The T90 time of both our free chlorine and zero chlorine sensor in our datasheet is stated at less than 30 seconds. Even at 30 seconds, that's a quarter of the time of traditional ampermetric sensors. And we've had a lot of customers and even some of our competitors test our device and say that T90 time is very, very conservative. They see almost instantaneous changes to chlorine measurement. We're talking 1 second or less. Very, very quick changes to chlorine. So we can be confident that we are going to be measuring peaks and troughs of chlorine, if any do come through, whether it be a carbon filter or a UV filter or something like that, whatever's supposed to be capturing the chlorine, we can be confident that we are detecting it a lot quicker than you would do with either a traditional ampermetric sensor or a colorimetric sensor as well. So if we were to have a closer look at the solution that we've just shown, you can see that we have two sample lines. We have the free chlorine and the pH sensor here. And then we also have the zero chlorine on the secondary line here. The reason why we don't have a pH sensor on the second line is because pH doesn't generally tend to change a lot across the filter. So what we can do is we can digitally link the pH sensor between the first line and the second line, and that will then compensate for the changes in pH and give us the accurate zero chlorine measurement if there is any coming through. We have on top here a polycarbonate enclosure, and this is where we would have things like the I/O systems, the Ethernet output, maybe like a data logger on there. We've got the 7-inch touchscreen display. We can also put things like a GSM module if you wanted to remotely connect to it as well. So we can put all that in a nice panel, mounted on a backboard that you just mount on the wall, and plug and play essentially as well. There's no reagent to replace for the pH chlorine and the zero chlorine. It's continuously online as well. We also have hot swap facility on these cubes as well. So if you needed to change over the pH, you could just take off the pH sensor. The two chlorine sensors stay online, put the new pH on, for example. So it is, it's a very fast process to take one off and put one on as well. So when we consider the traditional technology constraints that we looked at a few moments ago with all the traditional ampermetric probe, the reagent, the handheld units, our solution actually addresses a lot of those traditional problems. Now, our chip is an ampermetric sensor like we have with the ampermetric probe, but the difference is that we're not exposing the electrodes to the media. The ampermetric sensor with the chip is actually protected by a membrane. And that membrane is proven to be enough to prevent scaling, so we don't induce drift. We've actually got applications that have been in operation for over 2 years without any maintenance. And yet we've had customers, who have been using the traditional ampermetric probe, not just from ourselves, but from our competitors as well, where they're having to say we have to calibrate our probes every 12 weeks. We don't have to do that anymore with the MSO2. We've got applications that say typically have been in place for over 2 years without any intervention. And in fact, one of the case studies we'll show later on is a good example of that as well. For the free chlorine sensor, we don't have any electrolyte in there as well because we have an active pH buffer. We have an active pH probe. We don't use the electrolyte as a buffer. Also, instead of using the electrolyte as a protection to the electrodes, we've got that membrane on there instead as well. So we don't have to worry about replacing electrolyte in the free chlorine sensor. Now, in the zero chlorine sensor, we do have to provide a stable 0 point. And for that, we use an electrolyte. But the difference is it's not in front of the sensor. It's housed in a chamber away from the measurement area. So it's not impacting what we refer to as the T90 time. It would be, you would see a chamber on the side of the cube here that you can easily remove with just a quick release fitting, and then you can put a new one on. So the replenishment of the electrolyte is far, far quicker than it would be with a zero chlorine or free chlorine electrode that you would have from one of these over here. The zero chlorine sensor, yes, it's got electrolyte, but it's away from that measurement area, and that's really, really critical. I mentioned previously the active pH sensor also provides that pH compensation for accurate chlorine measurement and also zero chlorine measurement. We can see that the zero chlorine measurement is also stable for long periods without seeing any chlorine. Again, we've got applications which have been in place for a number of months without seeing any chlorine at all. And then as soon as a slug of chlorine comes through, we can detect it. And again, I've got another case study which shows, we've gone for weeks on end without seeing any chlorine, and we're still detecting very, very small trace amounts of it coming through the process. We also have low cost, fast installation and fast commissioning as well. For some of these trials that we're operating at the moment, we've plugged it in, put water to it, and we're seeing measurements that we can be confident of within minutes. It's as quick as that. Whereas traditional ampermetric probe designs, you have to have a stabilization time, kind of typically 24 hours, you'd want to continuously monitor it. Whereas with the MSO2 chlorine sensor, plug and play, and you can be confident in those measurements almost straight away. We're also not affected by pressure fluctuations as well. The membrane in there is not affected by that as well. We do measure flow on the system. So a lot of these systems, you'll see one of these flow sensors, typically our type 8031 paddle wheel. But it's just used as a verification to make sure that you've got sufficient sample going through, because we do need at least 9 liters per hour per cube. So that is just purely there. So if you were to come to us and say, we've got a problem with your sensors, the first question we will ask is, what is the flow rate through the cube? So that's why we always include a flow verification sensor on every installation. We've got that continuous measurement as well, the very fast T90 time, as you don't have with those traditional technologies. And it's also a very, very flexible design. We showed, how we can have some installations with just 1 or 2 parameters, or you can have some in there with 20 parameters if you really wanted. Yeah, it just depends on, what you're trying to do and how many you need. So the technology, I did talk about this sensor on chip design. That's what one of our chips looks like. It is what we refer to as a MEMS sensor, microelectrical mechanical sensor. Requires just 9 liters per hour. It's temperature compensated. We have the pH compensation from the MSO1 pH cube. We have high long-term stability. We have the protective membrane, which only allows the hypochlorous ions to get to the actual sensor itself. We have very low detection limit levels as well of 0.01. One of the applications I've actually got at the moment, we're actually measuring chlorine to 1/10 of that level as well. I mean, they're not verified, but we are getting measurements and readings, and we are quite confident about those as well. With chlorine dioxide, we can go to even lower levels, 0.01 ppm, but chlorine dioxide is it's much stronger disinfectant process anyway, so it's not surprising that we can go much lower as well. We have the calibration data stored internally on the memory, and we can measure fluids as low as 50 microsiemens as well. Some sensors require at least 100 microsiemens, sometimes even higher as well. But for the MSO2, we can go down as low as 50 microsiemens. So the first example I'm going to show to you now is a pharmaceutical application. This is for this is for one of our system integrators. It's in one of their demonstration locations where they can go, and end users can go and get hands-on with this particular solution. They can go and they can play with it. They can take the cubes off, have a look at the menu structures within the transmitters as well. And we are measuring both pre and post filter as well. So it's protecting the purification process, which is downstream. And each line, I must admit, we have gone over the top, but it's just to showcase what we have. We can see that we've got ORP, pH, chlorine, free chlorine, zero chlorine on each line, and conductivity as well. And when we put the system in, we realized that we could be confident in those measurements very, very, very quickly as well. We've now had repeatable results now for over 6 months without any intervention of the sensors. And within 24 hours, we were able to detect chlorine that was coming through the filtration process. And this is a snapshot from our communicator, which is a completely free piece of software that we have for all of our Bürkert products now. And what we're seeing on screen now is the free chlorine coming into the carbon filter. And the gray line down the bottom is post carbon filter. And you can see that that's been sitting down at the bottom quite nicely, zero chlorine, nothing coming through for a long period of time. Now we also have ORP, which is this orange line at the top, and it is below the threshold of 650 millivolts that we would expect for the presence of an oxidization species. And you can see that's absolutely fine. But then all of a sudden, we suddenly get a spike of just under 200 milligrams per liter, or 0.2 ppm, for a period of about 30 minutes, coming through the downstream chlorine process. And that's been verified by the ORP. It suddenly spiked up to 650 millivolts. Now, there is a time delay with ORP sensors because of the technology involved. So this is another reason why we don't recommend putting ORP as a method of detecting chlorine. Because it's not very reactive. It can also be influenced by other things, and you'll see that on the next case study in a moment. But you can see that we detected chlorine for about 30 minutes after the carbon filter. Now, as it happens, when we spoke with our partner, they said, well, actually, that's the backwashing process that they have through the carbon filter. And that's also going downstream, but it's not going to the downstream processes. That waste is diverted off to another process. So they can be confident that, yes, there is something in that backwash process, but it's being sent to drain. It's not going to get onto the downstream filtration processes that they have. So we can be confident that we are protecting and we are detecting chlorine downstream of this particular carbon bed. We actually repeated that a few weeks later. So you can see up in the top right-hand corner, 3 weeks later, you can see that the system was commissioned the back end of October. It's now mid-November, and we detect another spike in chlorine downstream of the process. So again, the red line is the incoming chlorine, the gray line is the outlet of the carbon filter, and we detect a spike in chlorine. Verified again by the ORP, but again, there's a delay on that ORP measurement. And again, yeah, we've got stable flow in there, which is the blue line. So again, we can be confident in the device sitting down at zero chlorine for long periods of time without having to worry about polarization or any degradation of the electrolyte or poisoning of the electrolyte, or any fouling on the membrane, fouling on the electrodes, because it's being detected by the membrane. So that gives it a very, very effective solution. And I've just removed the labels there for clarity. The next case study is a municipal case study now. And again, this is another demonstration system for evaluation by one of our partners in the municipal sector. And they wanted to look at this portfolio because they like the compactness of the system. Now, the installation they've put this on is actually on a recently upgraded municipal works, and it's monitoring the combined outlet from several ceramic membranes. So this is a municipal water treatment that's taking water from a reservoir, going through various different filtration processes through the ceramic membranes, and then onto chlorination further downstream. And on this particular trial system, we've got turbidity, we've got pH, we've got conductivity, we've got free chlorine and ORP. And when we plugged this in at the sample point, we had results within about 15 minutes, which we could be confident about. Now, also in part of this process, they use chlorine for backwashing the membranes, for keeping any biofouling of the membranes, keeping them clean and clear. So there could be an amount of chlorine which we detect. Now, this particular system has been in for over 2 months without any intervention. I actually had a look at the data this morning because we have remote connectivity to both this system and the previous system as well, so we can keep an eye on them. And again, the data is also very, very repeatable. And what we can see from the data is nice stable readings from pH and also from conductivity. The anomalies that you can see here have all been pretty much verified one way or another. The site was still going through a commissioning period. So some of these were changes to the software, the little blips that you can see on conductivity, the drops in conductivity. This was actually our automated cleaning facility, which is kicking in. So you can see that periodically gets in. So again, that's all been verified as well. But what has been interesting is the chlorine measurement. So the chlorine measurement has been sitting down pretty much constantly, because you've got to bear in mind that there's quite a few filters on this particular application. So there's always a trace amount of chlorine finding its way through the system, very, very low levels. That has been kind of coming through the system from all these different filters. And that's been kind of verified to a degree by the ORP reading, but you'll notice the ORP reading has been below the 650 millivolt threshold we would expect for the presence of chlorine. However, first of all, the amount of chlorine in there is very, very low. Very, very weak, kind of 0.01, 0.02 ppm. So it's very weak for starters. Now, the other thing is we also don't know what else is in the water, because ORP can be influenced by other things. If you have a reducing species in the water, it pulls the millivolt reading in the other direction. So if there hadn't been any reducing species, we probably would have seen this ORP reading up at 650 millivolts. But because there's likely a reducing species in there, it's pulling the millivolts in the other direction. So this is another reason why we can't trust ORP to give us a free chlorine or zero chlorine measurement, because it can be easily influenced by other things. But what was really interesting is the free chlorine levels sat quite quietly down the bottom for long periods of time. And then suddenly we get a slug of chlorine on the 25th of February, so quite recently. And that's also been verified. It's difficult to see, but the ORP did get up towards 650 millivolts, but not enough. Now, we have spoken to site, and site have verified this and said, well, actually, there were some people on site that was doing some maintenance, and they sent a big slug of chlorine through to disinfect the process. So this is verified by up here, and you can see that we've got a value 0.7 ppm, so quite high, going through this municipal works, but it sat quite happily down at low levels and then instantly detected the amount of free chlorine and a much higher concentration coming through the process. Just very briefly to finish, because I do realize that we have run over a little bit here now as well, but we are coming towards the end of the presentation. This is another global pharmaceutical application detecting chlorine, preventing an RO system. And this particular company, they monitored the downstream water from the carbon filter to make sure that all the chlorine had been removed from the process before it got onto the RO. And they run this particular system for about 2 or 3 years, and then announced they were going to expand globally on this particular production process. They have gone on now to install this particular sensor suite on all of their sites globally, to protect their RO, because they have that recognition that it is a low maintenance solution, plug and play solution, and is proven to be protecting the RO effectively as well in any EDI process, for example, that may happen downstream. And then another application, this time in municipal. This is Strasbourg Water. This is an application. I actually interviewed these guys personally myself a few years ago, December 22, and the guy couldn't. He was bowled over by how good our solution was, and how good it was providing the chlorine measurement across the whole of the drinking water network. And they still had some of the traditional ampermetric sensors across the Strasbourg network, and they're in a process of replacing those as they fail with our own solution. And he said, I have no problems with leaving this system for 2 years and not having to come back to it, not having to require any maintenance. He says every now and again I may just take a sample and do a verification. That's all that I need to do. He was that impressed with this particular solution. So, it just goes to show, customers are integrating this across their network. So to summarize, the MSO2, it's reagent free, it's electrolyte free. For the free chlorine, for the zero chlorine, yes, we do have electrolyte, but it's not going to affect the repeatability and the accuracy of the measurement, or the T90 time of the measurement. It's not also affected by chloramines. We've not really touched on chloramines. This is where the chlorine binds with bacteria and can actually become to a harmful process where you actually have to introduce more chlorine to chlor the chloramines as well. We're not affected by chloramines at drinking water levels, at least anyway. We have long-term stability, which allows us to provide reduced maintenance costs, and we quite often have customers reporting payback within 12 months because they're not having to recalibrate their sensors every 12 weeks. So it does offer some cost-saving opportunities for customers as well. Thank you very much indeed for taking the time to listen. I do apologize again that we have run over a little bit. Kirsty, are there any questions at all?
None in the chat box that I can see now.
Okay, that's not a problem at all. Well, hopefully then we have addressed all of the questions that you may have had. Please do send us an email if you have any questions or any applications you want us to have a look at. If you would like to get your hands on one of these devices, or if you'd like to have a trial, we can also organize that as well. But please do get in contact with us. I will now stop the recording. I can see there is somebody there